now we know for the expression the R is substituted by rho, which is a function of the radius as a variable. So that is 2z R over an A. Now, we are looking at hydrogen atom, all right, and we know it is a ground state n equal to 1. So therefore, immediately we can plug in for hydrogen atom z equal to 1. We're looking at the ground state n equal to 1, so this equals 2r over a. So we can substitute rho here with 2r over a, and then z equal to 1 here. We can combine the term with the 1 over 4 pi here. If we do all this substitution, what you really wind up for the wave function after all this combination, what you have is the root of a constant, pi s cubed. Then you times the e function raised to the power of r over a. Now, it's really nothing fancy. You just substitute the rho into it, and you combine those terms all together. So that is your exact. If I say, can you write out the exact expression for the ground state electron in the hydrogen atom? That is the expression. You plug in all the known values. All right, so that is your ground state. Okay, now how do we know the average or expectation values for the radius right here, the number 5, that's what we're working on. Then immediately what you're thinking about it is, this is a quantum mechanics class, what principle will postulate, what theory that I would like to use. All right, so now you're looking at it, the key word is expectation value. So to calculate the expectation value for any observable interest of omega, it's really to have an expression for, it's an integration of the state that define the system, and then we're going to multiply by the operator for that observable. Now the operator here is the radius, so therefore the observable is the radius, so therefore you're going to have an operator for the radius, operate onto your wave function, integrate along the space. Okay, so this is generic expression. Now we're looking at the radius. Now we know the quantum state for the electron is the ground state, so I can plug it in. So that is your ground state. Okay, so now in the generic expression for expectation value, we have the denominator term. But all the wave function for the electron in the hydrogen-like system, they are normalized. So therefore, you just divide the whole thing by 1, so no need to consider, you consider it, but the value is 1. Okay, now we already know the wave function because it's a ground state. We already derived it. Now we need to figure out what is the operator for the radius. We said radius, x, y, z, position operator, right? So the quantum mechanics will give you 2 operators. One is the position operator. The second one is the linear momentum operator. Now, position operator is just a multiplication of that position variable. Now, position can be in x, y, z or r, theta, phi. So therefore, this is a position operator. Now the position operator is really the multiplication of the position variable, which is the radius. And the operation is a multiplication. So therefore, that's how you substitute in. Now, furthermore, this is a complex conjugate operation. Now, if you take a look at the wave function for electron in the hydrogen-like atom, are they real function or they complex function?
It's a real function.
If they're real function, then make our life easy. Real complex conjugate of a real function just by itself. So you can simplify this. Now what do you see? In these circumstances, what you have is a wave function multiplied by the variable r, multiplied by the wave function, and then you do the whole thing with the integral. Now integral with respect to the d tau, because the electron motion is in three-dimensional space. Do you guys follow me okay? So what I like to do is, I can take it further, because this multiply, it can become a square. I mean, it's sine times psi is psi squared. Any questions on this? So far, we just do a mathematic manipulation. So let's write this clearly. All right, so this will be a d tau right here. Okay, now, if we do an integral, so let's write out what is d tau here. What is the volume in a three-dimensional space? Jordan.
X times y times z.
The d tau right here.
Oh, dx dy.
I would like to into the identify.
R squared sine theta.
So we will have the r squared sine theta,
dr d theta.
dr d theta d phi. So that is our d tau. So then you have a triple integral, right? I haven't done anything. I'm still going to copy this, the function, and then times r. That is, let's separate those. So this is your d tau value in terms of the spherical coordinates. So this is really your dx, dy, dz right here, right? And this is what we have here in this component, the multiplication in front of the integral. Do you guys have any questions on this? It's all good? All good? All right, now I know some of you take, so ideally calculus 3 should go all the way to, I say ideally, should go all the way through to triple integral. Now some of you may have gone through triple integral. Some of you may only gone through 2 or 1. Hopefully it's not 1. But if it's a 2, I'll show you exactly the same as 3. All right, so any questions? So far, we set up our expression through quantum mechanics, how to calculate expectation value. Now we just need to plug in the volume in terms of a three-dimensional space. Okay, all right, now let's plug in the wave function right here. All right. So what is our wave function? So you have a triple integral. Our wave function is right here. Now we're going to take a square right here. So what you have is the constant would be 1 over pi raised to the power 3 because it's a square. Then the e would be 2r over a. Any questions on that? That is your wave function squared. It's your wave function here and squared. Yes? No?
Yes.
Okay, good. And then of course I have this. Let's make it bigger. That's your operator for the that r is your operator for the radius. Any question on this one? Okay. And then excuse me, I'm gonna go slow because I just want to show you guys one time because this triple integral is gonna carry out all your calculations in chapter 8. So the sine theta, dr, d theta, d phi. All right. So this again is your d tau volume. All right. Now how do you guys do the integration? What do you guys learn? How do you do it? Separation of. Is it separation of?
Yeah, you could. It's one of the ways.
Separation. So now if you take a look at this wave function, only depends on which variable, guys?
R.
Huh? R. So then you can look at the volume term here. What do you have? Let me use a different. Let me rewrite this. Let me do that, and probably will be more clear. So this is your d tau right here. So I can group into the terms with r. So r squared dr, right? R squared r variable, right? What else? I have sine theta, d theta. Yes? Yes. Okay, what else? Then I have the d phi term. Just separate them. Okay, otherwise if I write it r squared sine theta d r theta, I just group them together with one variable. So r squared with respect to dr, sine theta, d theta, and d phi. That's your d top. All right. Now, if I want to, this is an integration, you have a limit, right? So the beauty that I can write on the board, I can erase it right now, right? But you guys have those fancy gadgets. So if I do integration if I respect to the radius, what would be the limits?
0 to infinity.
0 to infinity. Very good. Then I have the theta. What do I have? I'll tell you. 0 to pi. If I have a phi integration right here, what do I have?
0
0
to
2, right? Any question on this? All right, so then I have a triple integral. But if I take a look at it, I can separate them. Because my wave function, this wave function, not mine, this wave function, only depends on
R.
right? Only depends on r. So all I can separate with regarding to different variables. So how should we do that? It's just like the last time when we solving for the Schrodinger equation. Remember we also used the trick separation of the variables to solving for the Schrodinger equations for the hydrogen the electron island. So okay, so let's separate it into the integration with regard to the radius. Guys, how should I do it? You have an integral for the r from 0 to infinity, and I'm going to group all the terms rated with the radius together. There's a constant. All right, so let's make our life easy. Let's take out the constant first. The constant is just this guy, 1 over pi a to the power 3. That is the constant. Then what I have in here is I will have the integration regarding from the radius 0 to infinity. I'm going to group all the terms together. What I have in here is e function over r. Time that r is from our operator, right? And then what I have is the r squared dr. That's it. Yes? Okay, and then what I have is an integration regarding with the theta, which from 0 to pi. What terms can I group it? Sine theta, d theta. Jordan, do you agree with me? Okay, all right. So sine theta, d theta. What else do I have? I have the integration regarding with the phi from 0 to 2 pi. What do I have in here?
D
Pi. Very good. That's how we do. Okay, so you can separate from the double integral to 2 singles, or here we have 3 triple integral, and then we can group those all together. Any questions on this? Okay. If I don't hear that, then I'm keeping thinking about it. Should I explain more? Then we keep more, probably go slower than we could have done it. So if you guys think it's all good, let me know. Because ultimately when I'm teaching these classes, I want you guys to, to comprehend to some level, right? I told you, when I was an undergraduate, 99% of us do not really know what was going on. I'm not joking with you. Because they went so fast. He graduated from Berkeley, UC Berkeley, right? And then returned to my institution, so he speaks fluently English. I can beat him in verbal conversation, like say hello, where are you going? But he's fluent in, content in quantum mechanics. And the other thing is, he's so used to make a 10-page material into like 5 minutes in class. Okay, yeah, you guys should already know this. Let's just move on. So I spent a lot of time in the library as an undergraduate. I told you guys go Friday, go to the football game or whatever game of your interest. But when I was an undergraduate, boy, I don't have a weekend. I study all the time from morning to the night. In China, oh, it's interesting. In China, we live in the dorm all the way through from first year to the fourth year. You enter the first year, either you graduate in the first year or you kick out the program at the fourth year. There's no switching to one program to the other. It's a very different system anyway. So basically, we will group with the kids together in the one room, right? One thing is, here if you study, you still have a light. When I was an undergraduate, the light kicks off at 10:30. After 10:30, they have a switch in that building. Boom, shut off. So you can't use it. So what do we do if we really want to? We buy candles, we get candles just to see. Anyway, so what I was going to say is, I know how that feels. Therefore, when I teach these classes here, I want to make sure our kids to understand to a certain degree. But if you tell me you know everything, then I want you to teach it in the next class as well. So you're going to have some questions you're going to go home to figure out, okay? All right, now let's move on. So basically, you can separate those into 3 integrals. Now, if we take a look at it, this is from your calculation for the expectation for the radius. This is coming from the detail, but it doesn't matter. Those are all R variables. What can we do? We can combine those into R raised to the power of 3. Now, how are we going to do the integration then? Oh, I don't remember. I used to remember, but I don't anymore. But we have this textbook, right? Isn't this a normal integration? So I can write it on the top. So there is this integration that gives to you, let's see. Oh wait. If some of you can find the class very nice. Oh, right here. 0 to infinity, x raised to the power of n, and then you have the e to the kx. Of course, integrate with the variable x right here, and then out of the integration will be the n factorial divided by constant k raised to the power n plus 1. Okay, all right. So that is looking forward. We'll give it to you in your exam. Okay, now how are we going to do it here? This is just a generic from math, so variable is R. What is our variable here? This is x. Our variable is R, right? So therefore, correspondingly, the value of the integration is n factorial. N is the power with respect to your variable here. So therefore, what do we have out of the integration?
3 factorial.
3 factorial, okay. This will be 3 factorial, good. And how about in the denominator? So then we need to know what the k value corresponding to our scenario is, right? So R is equivalent to x in that expression. So the k is
2 over
2 over a, and raised to the power 4. Raised to the power of n. N is 3 plus 1. Okay, I think I'm happy. You guys are happy with that? Yeah. Okay, then how about this guy here? The second one. Regarding with the sine theta. Can you help me out?
Sine, cosine, sine, and cosine, sine. So it should be negative cosine.
So this will be out of right. Is it a cosine theta? Negative cosine theta? Of course you can use that book too, so but I'm just Yes, and I'm sure it is though. equal to cosine theta. Now how about this guy right here?
It's
You
just
think
5.
about this equivalent as it has 1 times this guy here. So the other integration is really what? If you really want to write, what you have it here is the 5 on 2 pi what? I think that's correct, right? Okay, so so now let's combine them together. There's really not much I can do about it, except this I can make it similar to the power of 4, 3 factorial. Oh, what is 3 factorial value is? 6. All right, that's as much as I think of. How about this guy?
That's 2.
This guy, if I think about it, has a negative sign. Then you have a cosine pi minus cosine 0. If I want to carry on, with me? All of this integration is negative cosine theta. Now I need to put the limits in there, right? The limits is the pi first, so cosine pi minus cosine 0. Yeah? Okay, now what is the value of cosine pi?
Negative 1.
Negative 1. Of course, I need to still carry that negative sign is coming from the out of the integral. Okay, so the negative 1 minus 1. So what do we have?
2.
Negative 2. You have a negative sign right here. What do you have out of the integration for that cosine?
2.
2. Very good. Now how about this guy? This guy really means is 2 pi minus 0 because you can plug it in the pi, right? Pi from 2 pi minus from the lower bound, that's 0. And what do you have out of the integration?
It's just
2
2.
pi. All right. Very good. Okay. Okay. All right. All happy? Okay. Now, all right. In the future, there's a shortcut. If you guys can see an integration of the angles with no other stuff, just by itself. What will be those two integral values going to look like?
It'll be 4 pi.
Pi. You take shortcut on it now. You don't really need to show everything. So that is literally is 4 pi. Okay, if we all got this right away, I know I'm going a little bit slow, but I think it's a good thing. So this is really equals to 4 pi. And then what else I have is I still have this constant term, so I'm just carrying it over. Right, so I have a constant, didn't do anything. First integral, single integral regarding to the radius, that is the value, and the product of two integral with the angle is 4 pi. Okay, after this it becomes algebra, right? It's algebra because you have pi got cancelled. Alright, now what I also have, I have an a to the power of 3. What do I have it here? So if I want to change this, so this will be 2 raised to the power 4. Then you have an a raised to the power 4 in the numerator. Okay, now a combine the a term, a raised to the power 4, divided to a raised to the power 3. So it will reduce to a raised to the power of 1. And then you have a 4. Oh, let's don't do too fast. So 2 raised to the power of 4, what is the value?
16.
16? Alright, now 16 equals 4 times 4. Yeah? And then 6 over 4 equals 3 over 2. So what is your solution?
3 over 2.
3 over 2A. Okay, it's all worth it. I'm glad I go through with you guys at least one time to show you if you didn't get a chance to do the equal integral. I just walked through with you. Now, of course, I did some silly slow step algebra, but that's fine too. Alrighty, now you may ask, I'm interested in the radius, average radius, you have the A values right there. And I still don't know, I want to get the number, because once we see a number, we feel like, okay, that is a value. And if we have a symbol, a lot of time we're like, oh, I'm not sure what that is, right? So, alright, so if we take a look at this, A is a constant. We said A is a constant. Alright, what is A value, guys? A equals to the ratio in terms of A sub 0 is the mass of the electron versus the reduced mass. Alright, now A naught, you guys know that value, equals to 52.7 here. That's a distance. That is a distance for the electron in the hydrogen atom, that away from your nucleus. Now, what is it? We know millimeter, right? These are the standards. I think in the US, we use standard unit to indicate the length, right? You guys like inches and foot and yard, right? But in science, a lot of time, we use SI units. So we use meters, centimeters, millimeter, picometer, nanometer, etc. So the PM, how do we convert it to the meter? 10 to the negative 12 meter. So this will tell you it's about 0.52 angstrom. Angstrom is 10 to the what? Negative 10. Is that right? Alright, anyway, so what I'm saying is A naught is a value. So you can just remember at the 52.7 here. Alrighty, now how are you going to do the ratio of the mass of the electron versus the reduced mass? We say we consider a system of the orbiting motion of the electron with respect to that nucleus, right? Nucleus. So therefore, the reduced mass is calculated with the 1 over the mass of the electron, then plus what? Mass of the nucleus for that hydrogen atom. Now, if the one of the mass is so significantly smaller than the other one, then the whole thing can be approximated. You guys can go home and try it. You know the mass of the electron, you know the mass of the proton, the nucleus for the hydrogen atom. But what I'm going to tell you, the reduced mass for the electron in the hydrogen atom is very, very close to the mass of the electron. You can go home and try it. I mean, we showed it in class at the beginning. So one is the power 10 to the negative 27 kilogram. The other one, the electron, is 10 to the negative 31. So there are 10,000-fold differences. So therefore, that approximation is pretty valid. If that is valid, what do you have it here?
It's just
The constant A just equals to A naught, which equals to 52.7. Excellent. Here. Okay, that's how we do. Alright? Do you guys really do not remember the electron in the hydrogen atom in the 1s orbital? Its average distance is 52.7. Okay. Now you know. Okay. Alright, where are we? That's a lot of work, but it's all worth it. Okay. Alright. How about we do the number 3? I'm going to give you guys 2 minutes to think about it.
number 3.
2 minutes. Can you guys set up the expression? What is number 3? Write out the explicit expression to calculate the excitation value for the potential energy of the hydrogen with the electron in the 1s orbital. The reason we say the 1s orbital because the electron can be defined by the whole series of a quantum state, right? Defined by those 3 quantum numbers here. So you need to know at which quantum state it will have the different value. If the electron is the 100, the average value is not the same as 200, 300. Okay, so now you say at this particular quantum state, can you set up the expression? Now this, you guys probably be happy in some way to see a question like this. Why is that? This does not ask you for
The answer, the
a
solution,
final answer. What is asking you for?
to set it up.
As long as you can set up all the way to here. That is all asking you for. Okay. Alright, so let's give it a try. I give you 2 minutes. How should we do this differently? So what are we looking at it right now? We're still looking at the expectation values, right? Except if I want to make a change in here, it's no longer the radius. What is our observable?
Potential energy.
It's our potential energy, very good. Okay, and then, of course, I'm going to rewrite this in terms of potential energy. So I'm typing here what you're saying. I have a wave function, which is 100. Then I need to come up operator for the potential energy, operate onto the wave function, you do the whole integration, with respect to the space. So let's erase this guy here too. We need to pick up. We need to pick this one up. Okay. Now, what is our operator for the potential energy?
1/2 kx squared.
It's in the Coulomb potential, right? The electron is in the, right? So we said this is our nucleus. Electron is right here. This is a negative charge. That's your positive charge. And we say the nucleus at the origin, and the electron orbits around that nucleus. And the distance between those two are the radius. So there are 2 charged particles. So the electron is in this Coulomb potential. So then what is our potential energy operator if it's a Coulomb potential? So very good. It's E squared over we went through 2 or 3 times previously discussed about this potential energy. Okay, all right. Now what do we need to do, guys? We need to, the same, it doesn't matter, it's a real function, so it's the same. And then this is our operator. You just need to plug it into it. What kind of operation is that? It's a multiplication. If it's a multiplication, I can A times B times C, I can do whatever order I would like to. But that's not always true if you have a derivative. But multiplication, everything should be easier, so therefore I can combine the term again. I can combine it. The side here is a multiplication. This multiplied by this guy and multiplied by that, and it can combine with the square. Then what are happening here is E squared over 4 epsilon R T. That's it. That's it. After that, you guys are going to do the one whatever we did. Okay. Then you just follow. You do the similar thing. Now what you do is just combine it and come up. Of course, this will no longer be like this anymore. You guys are going to figure it out. Make sense? Yes? Okay. Alrighty. Now, I will give you guys this problem. Okay. Now, what if the system, instead of we want to know all those average positions, the average potential energy and so on and so forth for the ground state. Now, what if we have, let's say, in an excited state, uh, 211. And I'll come to you. So let's say I have the same question. I want to calculate the average radius with the quantum state of what? 211. What do you guys think? How is that different? Or the same? I would say the idea how to execute the problem is exactly the same. No, what would not be the same? Yeah. Yeah. So now I will have 5 made no longer is the constant interval, right? The 5 will be represented by a e function. So therefore, when you separate, you may have a different component regarding to the d theta and d phi. So mathematically, just add a little bit complication. That's about it. And I think that is the whole thing regarding with the math. Math is really, really, really important. Okay, but first come across is we need to set up with the expression, and then we will bring in the math component. I have many people raising their hand, and then now they're turning on this and all over the place. Let's start with you. What is your question?
For that potential energy, or that you have up on the board, is that still going to be a triple integral, or is it be a single?
This one?
Yeah.
What do you guys think?
Still has to stay triple.
Triple. Right, because you have a theta right here. Except the wave function for the angular component 0, 0 is a constant. So no matter which theta and the phi value you're looking at it, it's exactly the same value. Okay. Did I answer your question? Okay. Anybody else? Yeah.
So our potential energy on 211, we have to include the L plus L plus 1. The second part of the potential energy.
This one?
Not the cont.
Oh, I see. That is effective potential energy. That is not the potential energy for the electron in the system. That is the effective potential energy when we do the separation of variable, including the angular component.
Okay.
That is the effective, not the potential energy.
What about for phi? So if it's 1, plus 1 and minus 1?
So,
like ML would be.
so for the potential energy of the system, the electron is under the Coulomb potential. So that is the potential energy of the system. But I see what you're saying. When we're trying to solve it for the Schrodinger equation, we want to separate the angular component from the radius component. We want to make the radius component looks very similar as a one-dimensional Schrodinger equation. So we group the term together, make those two together as an effective potential energy. Okay. And so you had a second question. Go ahead. What is your second question?
So for the.
No, I think sorry. Same thing? Okay, yeah, go ahead.
So for the potential energy of the ground state, we still just take the integral with respect to r and multiply that for pi.
Oh, yeah. Of course. Sorry, I didn't go that because it's just, I shouldn't say just, but in algebra, right? Yes, of course. But I don't want you guys to get confused because this r squared is from the deta. The volume term, integration to the volume. This R is from the potential energy, the operator for the potential energy. So you need to come up all of this. Then after that, of course, you're going to simplify and regroup and do whatever you need to do. Absolutely. Is that your question? Any other question? So you basically saying is this at the end will be canceled to this guy. Is that what you're saying?
Say that again?
Yeah, basically you're
Yeah,
saying.
you can cancel
Yeah.
it.
Of course. You need to figure it out. Any other questions? Yes.
Did you put that formula for the potential energy on the sheet? 'Cause I don't think
It's not on the equation sheet.
I don't think so.
Not.
Do you guys want it? Yeah, then I can put it on. That's really not a problem. Oh, we can come up. It's just a coolant potential, right? With the two charged particles. But I'd be happy to put it on. That's not a problem at all. Any other question? All right. So if it's not, now let's briefly go through those questions. All right. How about number 2? What is the magnitude of the angular momentum for the electron in the ground state? You know, the electron is orbiting around the nucleus, so has the orbital motion, right? So how do you calculate the angular momentum value? So when we examine the particle rotation on the sphere, remember how we're going to get the value for the angular momentum, J? Right? We will have a linear momentum, and then we will have angular momentum, Q. How do we know the angular momentum value?
The square root of
That
L.
equals to the square root of L plus 1 times the constant h bar. All right, now the rotation, it's like I'm walking in 3-dimensional space. I have a linear momentum, right? Linear momentum in the represented by p, it will have a px, py, and pz in all 3 axes. Same thing. This is the total angular momentum. Then it will also have the 3 components. Okay, I really need to hurry up because I want to finish this one. I don't want to drag it to the next lecture. So how do we calculate the z component of the angular momentum? Very, very good. It's equal to m sub L h bar. All right. Now for this electron at the ground state, for the hydrogen atom. The angular momentum is only related to the angular portion of the wave function, which is your y function. So what would be our j value? Wow, you guys are fast. So you guys can dismiss the now. Let's see, it's a 2 minutes. Why is 0?
This L is 0.
But give me goosebumps. So how can your professor only know 1% in the class and you guys know 50%? So you guys better show me in the exam corresponding to that. No, but I don't want you guys. Your professor is actually super smart. You know that, yeah? All right. So the 0 L is 0, so 0 plus 1.